This is This Week in Science and Education, Episode 19, The Best Of. It's time for This Week in Science and Education, the internet show that talks about research, science, and news, and how to take that information and apply it into today's classroom. On today's show, we're all on holidays. But don't worry, we created a Best Of show just for you. All that and more coming up next on This Week in Science and Education. This Week in Science and Education is brought to you by Mueller Systems. Need a backup? Check out MuellerData.com/VROC for your free 90-day trial. And by Polycom, world leaders in unified communications. Polycom.ca. Hey everybody, welcome to a special episode of This Week in Science and Education. Well, Colin, Thomas, and I decided that we were going to take a little more time off during Christmas and New Year's, but we didn't want to leave you hanging, so we decided it might be fun to clip and put together a Best Of show. So we have 4 clips from 4 different episodes that we've completed over the past 4 months. Had a lot of fun doing it, and they are coming up next. The first one we're going to look at was episode 19, and it was a grade 6 student. Her name was Emma, and she talked about biodiversity. Here she is.
Let's get right to our guest because she's sitting very patiently, and I know everybody out there would like to talk to Emma and find out a little bit more about her project. So, Emma, how are you? And welcome to the show today.
Okay. Hi, my name is Emma. I'm in grade 6. I'm 11 and 3/4. I'm going to talk to you about my project on biodiversity. First, I'm going to tell you what I believe the definition of biodiversity is, why this is an issue on biodiversity, some positive and negative impacts on the environment, and my plan to help to fix the negative impacts. The definition of biodiversity is how different ways on how living organisms live, such as different varieties. Like a lion, they hunt for food, live food, and then they eat it without cooking it. But humans, they go to the grocery store and cook it on the stove and eat it. What I did is the nuclear power plant. How it works is they take uranium and they make it into these control rods. You may not be able to see them, but they're 4 sticks, and they are put in the reactor core. It creates a lot of heat, and with that heat, water gets surrounded around it. And then the water creates steam, and heat rises, so the steam goes up through this tube here and turns the turbine, which powers the generator and goes into the hydro towers. And then the wires from the hydro towers goes into the hydro pole, and then through this wire into our house. And inside the house is a stove. It gets powered by electricity, and we use it to cook, to eat in our different ways. And here a television it's used by electricity, and it is used in different ways, such as to entertain yourself or video games. And up here is a light, so we can see. And a positive impact on the environment is it does not create any air pollution or no greenhouse gases. But there are some negative impacts. A negative impact is that it creates radiation. After the uranium is used, it makes a lot of it, and then if there were to be any accidents anywhere, a lot of living organisms would die. Also, it kills a lot of fish and their eggs. What happens is they suck in water from Lake Ontario to cool down the steam, because if you don't cool down the steam, it'll just explode, the power plant. And so then they put the water out at a warm temperature, and it's at a warm enough temperature that it's able to change the water climate. which kills more fish because fish are very sensitive. I know that because I've had a lot of fish and they all died because of the temperature. Now,
Okay.
my plan is to tell a lot of people about this, and hopefully they will save more energy. But what you can do is you can turn off the lights, turn off the TV, and you know how it's Christmas and you have all these lights? Get a timer so it turns on and off during the day. I hope you learned a lot, and thank you for your time.
Thanks, Emma. That's a great presentation. We do have a few questions for you. Will you stay on camera for a little bit so we can ask you some questions?
Yeah.
Super. Okay. I guess the first question I had is, how did you come to decide to do a project on biodiversity?
Well, my teacher, she assigned it to our class, and then I decided to do the nuclear power plant.
Okay. And how did you had to conduct some research and find out some facts and things. Talk a little bit about how you got all the information together for the project.
Okay, well, what I did first was I just went to Google and typed in issues on biodiversity, and I found the nuclear power plant. So I thought it was pretty neat, and I also thought that it's pretty unique too, and not a lot of people will use it, so I wanted to do it, so it'll be original.
Isn't this great, guys? We've got a grade 6 student, doing projects on biodiversity, learning about nuclear power plants, primary source of information, those Google, you notice that. I'm sure that's everywhere in the classroom. What do you guys think about this?
Have you ever? I can't even speak now. Did you ever go down to the power plant? Like you're in an area that there's a nuclear power plant not far from you. Have you ever visited and taken a look around at some of the tours they do there?
Well, sort of. There's a walk near a windmill,
Yeah.
and I think it's near the nuclear power plant is near there.
Yes. Yes.
So,
So you've wandered through there then?
my
Excellent.
family.
I have a question. As you're setting this project up, one of the exciting things for me listening to it was your enthusiasm about the project. Was it part of that enthusiasm because you know where the nuclear power plant is, and this is talking about Lake Ontario, this is an area that you know about. So how much of this being a global issue, but something that locally you're aware of, did you think about? I mean, does that play into you being excited about it, that these are things you can relate to?
Yeah,
Okay, good, thanks.
So you had some fish that were affected, you think, by high temperatures in the water? Talk a little bit about that.
Yeah. Did you actually do an experiment, or is this just something that you let the heater go too high in your aquarium and noticed it? How did that come about?
Well, it was on the internet.
Ah. So
Yeah.
it must be true then.
Yes, and I've experienced several times with my goldfish.
Okay. How did you experience it?
Well, we got fish, and we didn't really know that too much, so we just put it in a regular tank with whatever water. So
Right.
it must have affected them because they need a certain temperature. So they just all died.
Okay.
Do we know that the temperature in this particular case, so in Lake Ontario, could you find information that said that it is actually killing fish?
Yeah, I could. Yeah, I did.
What did you find?
Well, I found it kills 1,000 fish, I think, per hour. Whenever it creates electricity.
That's a lot of fish.
That sounds like a
There's
lot.
a lot of fish. Yeah.
So Emma, the other kids in the class, were they all doing similar projects, or did you all pick one topic and do something different?
We all picked one topic.
Okay. And so you picked this one. Well, we're really glad you did, and we thank you very much for coming on the show today and sharing your research project with us. And maybe I noticed you logged a question on the website. We'll have somebody log on and answer that.
Well, let's take a look at that.
Okay, let's take a look at it. So you can't leave yet.
No,
Don't go.
No.
Maybe we should just read it for folks that.
Sure. I'll read it because I've got it right in front of you. I won't read it all, but the first part is talking about your project. But then you were wondering if about more about the positive and negative impacts on your topic, and you were thinking about creating posters to make people aware. And is there any ideas that we have to help, make people aware other than posters? So there's actually a couple of questions there. What do we know about the positive and negative impacts, and ideas about how to make people more aware of it? I'm going to start by asking you another question, Emma. Have you thought about other ways you could make people aware other than just your poster like you have behind you? Have you thought of other ideas to make this more known to people in the area?
Yes, I actually plan to do this. So yeah, because you said that people across Canada watch it, so maybe that'll make them think about it, about turning off their lights next time they leave.
Serves you right, Jagoe.
A little multimedia, right? The obvious answer, yeah, you guys. Well done. No, good for you. Good for you. Did you present this to your class, or was it part of a bigger science fair? Was there more people involved than just your classmates?
No, I just presented in front of my class.
Okay.
Well, one of the ways we might be able to help you get the word out, Em, is if you want to provide us with some more information, we can put it up on the VROC website and put it in the show notes area, and that way when other students go to the website, they can learn more about your project and the important information that you're sharing with us. So if you get that over to us, we'll make sure we put it up there, okay?
Okay.
Another. As I sit here and look at it, another question pops into my mind. You're asking about the positive and negative impacts. What would you do next, right? You've discovered that warmer temperatures is killing fish. Is there any ways of going about finding out more about that you've thought about, or what could you do as another project in addition to being aware of it, but sort of getting into maybe of a more science end of things? Any ideas about how you could go and investigate this a little bit more?
Well, I guess I could look on the internet for like a phone number for the people who work there and ask them a few more questions about it.
Sure.
And books.
I'm sure they have data, yeah. And fair enough. Okay.
That's the educator coming out in you, Jagoe.
What? Asking for more questions?
Absolutely.
Yeah. What would you do next? That's always the question. What would you do next, right? Because has there been any other questions that have occurred to you in addition to the ones you've posted here? Like questions you have about the whether it's the nuclear power plant or impact on biodiversity itself. Is there any questions that have come to your mind?
No.
I think Thomas had a question. Go ahead, Thomas.
Let me ask. So, Emma, as you were going through this, you probably had some idea what biodiversity was and what nuclear power was or is. What did you find most surprising when you were doing your research? What was it that really caught your eye and something that you didn't know before you started this project?
Well, I saw this link that said fish dying. So then I clicked on it and I saw it was because of this. So then I started looking at it and stuff.
That's great. Thanks.
We're talking with Emma, grade 6 student, about her science project, biodiversity. And Emma, before I let you go, just tell us one more time what we can do to help with this at home. You mentioned turning off lights and things of that nature, but what are some other things that we can do at home to help?
When you know how it's Christmas now and you just leave your lights on, we should try getting a timer like I have, because so it turns off and on when you want it on and off. So that actually saves energy.
Great.
By a lot.
Do you know, and where do you get those timers? Do you know?
Canadian Tire.
Free plug for Canadian
That's
Tire.
right.
There we go.
That's right.
All right, Emma. Well, thank you very much for coming on the show today. It was a
thanks
lot
for
of
having
fun
me.
having you. Oh, you're very welcome.
Thank you.
Take care, and we will talk to you again soon in the future. And make sure you send us that information for the website, okay?
Okay. Merry Christmas.
Great. Bye. Merry
too,
Christmas.
Emma.
Bye, Emma. Thanks again.
Bye.
Hope you enjoyed that clip with Emma. We certainly did. The next clip that we have for you is from episode 17, entitled Triumph and Isotopes. And in this interview, we talked to Dr. Marcello Pavan. He had some really interesting information to share with us about the so-called shortage on nuclear isotopes, but also some very exciting news for Alzheimer's patients. I hope you enjoy it. For the full episode, check out vrock.ca and look for T-WiSE episode 17.
Pavan, nuclear medicine, isotopes. We heard a little while ago there was a shortage. What's the latest on that news story?
Well, the latest. It's an ongoing saga. Let me give you a little bit of background. What we mean by the isotope shortage is we mean one particular isotope. The whole field of nuclear medicine involves using various kinds of isotopes, radioactive partners of normal atoms, like radioactive carbon rather than normal carbon, radioactive nitrogen rather than normal nitrogen, etc. So there's a whole bunch that are being used in nuclear medicine today. Iodine, you may have heard, you get the iodine cocktail or the barium cocktail, and they take pictures. But 80 to 85% of all nuclear medicine procedures involve this one isotope. It's called technetium-99, M. And about 90% of the world's supply of this isotope for nuclear medicine comes from two nuclear reactors. One of them is in Chalk River in Ontario, northwest of Ottawa. And the other one is, I think it's in Belgium or the Netherlands. And what happened was, some time ago, is the reactor in Chalk River is very old. It's from the 50s, and it was starting to, show its age. And so they had to shut it down for an extended period. Now it's basically half the world's supply of this isotope, which is, again, used of all procedures. It's about 80-85% of all procedures. So it had a significant impact on doctors because they were used to using this isotope. So the Chalk River they saw this coming, and so they built they were starting to build two new nuclear reactors called the Maple reactors. And then they had some safety issues with them. The Canadian Nuclear Safety Commission wasn't happy with some of those issues and how they were being dealt with, so they literally shut the things down. They stopped the project. It's in stasis now, the last I heard. And so what you had a situation now, so all these doctors used to doing nuclear medicine procedures, half their supply was just gone. There isn't any place in the United States that does this because they thought we were going to do it, essentially. The thing about it is you can make it other ways, and there's other ways to do the same things. So into this mix, various people step forward, including Triumph, to try to come up with other ways to fill in the gaps, and also to come up with new techniques of making this technetium that do not involve nuclear reactors. Because what's little known is that one needs weapons-grade uranium in order to make this technetium. So the United States ships weapons-grade uranium to Chalk River. They put it into the reactor. In the reactor process, when the uranium splits, about 6% of the time, you get this isotope called molybdenum-99. And then the molybdenum-99 decays into technetium-99, and then that is what's then used in hospitals. There's a whole supply chain that's been perfected over 50 years or so about how that all works, and this was disrupted at the front end. So, and the United States has been making noises like maybe we don't want to be shipping all of this weapons-grade uranium to Canada. You figure, huh? So, because even after they use it, and they take it out and it's, so-called spent fuel, it's still weapons grade uranium, right? And it's sitting in barrels in the backyard in Chalk River. So long term, this is not exactly a situation you want to keep going for in the long term, right? So lots of things are happening. The federal government announced some funding to address this problem. And just recently, there's been, they awarded some of these monies, and Triumph got some money, and I think it's around the order of $6 million or so. And that was to investigate using accelerators, particle accelerators, to create this molybdenum-99, rather than using a nuclear reactor. So we got this money to try to make a proof of principle. Well, we had earlier money to make proof of principle. Now we're getting money to see if we can actually commercialize it. Other research groups, including the NRC in Ottawa, got also some money to look at alternate ways of creating this technetium using electron beams. So there's a multifaceted approach happening. And a number of research groups are attacking the problem right now. But this is not a short-term solution. This is a medium to longer-term solution. Assuming the supply of weapons-grade uranium stops, which is not at all inconceivable, then we need to find a way to do it. Now, these accelerator-based approaches are mostly going to be at a regional level. You have an accelerator, supplying a region. The lower mainland in Vancouver, or, the 405 belt in Vancouver, in Toronto or something. So it won't be like shipping it globally. So that's where we are right now. There's also a movement afoot to use different isotopes based on positron emission tomography to do the same things that the technetium would have done. And in fact, they could do them better. So there's a big movement. Tom Ruth here at Triumph has been spearheading this to try to show everybody, say, hey, we know you're used to doing this for 50 years, and that's great. You know how it works. But hey, if you do it this way, you can actually get better results. So things are slowly moving, and I don't think it's a crisis anymore. The reactor is back online, but what is it? Once scared, twice shy. What is it?
Yeah. Once bitten, twice shy.
Yeah, once bitten, twice shy. So they got bitten, and so now there's making plans. Just to make sure this doesn't happen again.
Yeah.
Michael, let me ask a question before we go on. I'm sorry if I just missed this, but assuming that my countrymen could actually do this, why are the Americans shipping the weapons-grade uranium here rather than creating the medical isotopes in the United States?
Good question.
Good question. Because I don't know the long history of it. I asked Tom recently about this, and he said, the technique, this whole supply chain technique of how getting the technetium out of the molybdenum, which is created in reactors, was actually developed in Brookhaven, which is on Long Island. And,
I live 20 miles from there.
Yeah, okay. So then it just started Canada started to do this at Chalk River, and they were doing it well, and they figure, well, they're doing it, and instead of us building a reactor to do this, why don't we just ship them the weapons-grade uranium? Because they get it all back anyways. They ship the uranium here. We create we look at the isotopes, create the isotopes. They get the product, ship it back to the States for processing, because they're the primary users, right? So, the history of it, I'm not exactly sure, but once it started working, once it was stable, they figured, well, just, keep it going. They actually made a decision. Go ahead, sorry.
Sorry, I have a crazy question then. We're talking about shipping this weapons-grade uranium. How exactly are we shipping this? This is not going FedEx or UPS. How are we getting this stuff?
I don't know. It's probably by train. Certainly can't fly it, right? It's probably by train, and I'm guessing that they're not going to tell you exactly when and where.
They're not going to tell us.
I don't know.
Oh, that's funny. So, have we had an issue in the Canadian healthcare system or North American healthcare system with the shortage of the technetium isotope then?
As far as I know, not. I mean, there was a great amount of anxiety, and clearly there was procedures canceled, and I haven't seen anything, a detailed study about what this might have meant in terms of medical outcomes. I haven't seen that. But what I did learn from talking to some of the real experts in this field is that they said that the doctors started to modify their procedures. So, for example, one of the things that ameliorated or made the problem a little bit less bad was they realized that they were wasting a lot of this stuff before. It was always there and it kind of worked, and they were kind of wasting it. And so they were a little bit more careful with the management of the resource, and so that helped the problem quite a bit, actually. Yep. And then they were looking to these other techniques like positron emission tomography to try to fill in some of the gaps. So they were, reassessing and being a bit more efficient, trying other things, and so that more or less kept the crisis from becoming a really, really big problem. But undoubtedly there were some issues. I just don't have any sense of really the scale of it.
You mentioned the particle accelerator approach as an alternative to the nuclear reactor, and you said something about it's a long-term solution. I'm wondering, by long-term, are you talking months, years, or decades, or how long is long-term?
Years.
Or
yeah.
Even okay.
I think it'll be well, not months, but maybe a couple of years until they could show the proof of principle to make it work, get the system up and running. There are things about purity of the sample. So you make the stuff, is it pure enough that you can inject it into patients? So there's a whole supply chain issue of how to, because you're injecting this into people, so you have to make sure the product is pure and clean. You have to make sure your processes are reliable. That takes a little bit of time. So I'm thinking probably years, not decades. By a decade, this should be online. Maybe not widespread, but at least online.
We're talking with Dr. Marcello Pavan from Triumph in British Columbia, Canada. Colin, I know that you're not on camera, but you are here audio-wise, so I can't cue you visually. But feel free to jump in. What do you think about all this?
Well, it's very cool. I was just wondering, maybe a bit of background might be useful for people. We talk about we put these things inside of us. What do we do that for? How do we actually use these isotopes?
Oh, okay. It's basically from imaging, taking pictures of inside the body. Mm-hmm. So the technetium is, what they do with the technetium is they create technetium oxide, TCO4, I think it is. And they inject it into the body, and then they primarily used for imaging the heart function. So cardiology, but that's most of what they do. So if you want to take a picture inside the body, you can do X-rays, but X-rays can only show you structure. CAT scans show you structure of the body. They don't show you muscle function. They don't show you how well your thyroid's working. So they use iodine, put it into your thyroid, and and what you do is you detect the radiation coming out and trace it back to where it came from. So when these isotopes decay, they emit radiation, they're detected, and you're able to then trace it back into the body and find out where they came from. And so the iodine goes into the thyroid, and they know what the picture should look like for a healthy thyroid. And if it's way too bright or there's not way duller picture than it's normally, or maybe half the size that it should be, then there's something going on with your thyroid, and you don't have to cut yourself, don't have to cut you open to look. In positron emission tomography, they have developed other isotopes, including fluorine and carbon, where they attach to biomolecules in your body, like glucose, like sugar. Okay, so they inject it into your body and wait for these atoms on these biochemicals to decay, because the biochemicals, just because they have a radioactive atom on it, doesn't mean anything. Chemically, they behave exactly the same way. So the glucose will go to your brain or do whatever it normally does. It doesn't care that it's radioactive. When it decays, you detect the radiation, you can see where it went. So for example, you give somebody glucose, radioactive glucose, if you have a cancer in your body, cancer eats a lot of sugar, a lot of glucose. So if suddenly you take a picture of the body and there's a spot on your liver or something, or on your bones, where there's a big hot spot where there's a lot of this glucose going there where there shouldn't be, then you know, oops, there you got cancer. And in fact, that's what they're doing at UBC Hospital, at VG8, not UBC Hospital, Vancouver General Hospital, is they study these cancers, and they actually use them not only to diagnose the cancer, but in the treatment. So they could say, oh, this person has cancer, and we could see the picture of where the cancer is from this technique. And then they do their treatment, and then they keep taking pictures to see if the tumor shrinks or it doesn't move. And if it doesn't move, then they can say, well, this isn't working, stop that, try something else. So this is a method to be able to look at what your biochemistry is doing by taking pictures without having to cut you open. Similarly, you can use neurotransmitters. There's something called fluorodopa. It's a dopamine. And you can look at how your brain functions. So they use it for studying Parkinson's disease. So they can actually see your brain in operation. They can see where the dopamine goes in your brain. And Parkinson's patients, it just doesn't function the same way. And this is actually very exciting, and I'm sure the listeners would love to hear this, is now they have managed to find a biochemical which is a terrific biomarker for Alzheimer's disease. So now they can give you a biochemical, and if you have Alzheimer's disease, it attaches to this white plaquey substance that goes into the brain, preferentially. And so if you take a picture and you see okay, let me back up. This stuff won't attach to anything else. So if it goes into your body and it doesn't have anything to attach to, then it'll just get flushed out and then you won't see anything. Right. If you do have Alzheimer's, it'll get stuck to this whitey plaque, and you take a picture and then you see it. You see the radiation coming from your brain, and you say, aha, that person has the white plaquey stuff associated with Alzheimer's. This is the only technique known today to be able to diagnose Alzheimer's in living patients. So it's hard to treat something when you can't see it. So now they're really hopeful in a couple of years this is going to completely change Alzheimer's research, because now you can see it. And so you can, give some treatment and see if it gets less, and then if it doesn't, try something else and, watch it shrink and grow. So now you, like they say, they have a knob to twist, have something that they could look at. So it's very exciting.
That's really exciting. Just from my own personal experience too, grandfather with Alzheimer's, and there's so many people that suffer from that disease, and it's such a terrible disease too. That is really a nice glimmer of hope. So thank you for sharing that with us.
It really is.
Our next clip is from one of our most favorite shows that we've done over the past 4 months, and I think I speak for Colin and Thomas in saying that our visit to Sudbury at the bottom of the Crichton mine in the snow lab was probably the highlight of the year so far. On that day, we traveled 2 miles down beneath the Earth's surface and then another 1.5 kilometers to get to the snow lab on foot. Once there, we were treated to viewing some of today's scientific experiments that, well, for lack of a better way of explaining it, were just absolutely fantastic. This short clip, well, it's not that short, I guess it's about 14 minutes long. We wanted to include as much as possible. But this clip with Dr. Nigel Smith really tells the story of the Snow Lab and the incredible research that's being conducted there. I encourage you to go to vrock.ca, check out episode 16 entitled The Snow Lab for the full story, but here's a little teaser.
Dr. Smith, maybe you could tell us a little bit about who you are, what you do, and what the Snow Lab is all about.
Sure, okay. So I'm Nigel Smith. I'm Director of Snow Lab. And Snow Lab is a deep underground facility. So it's a place where we do lots of different kinds of science, but we do it at the bottom of a hole. So we're 2 kilometres under the ground, and as you say, we're in the Crichton mine in Sudbury. So we're very pleased to recognise Vale, who are the mine operators. This is a nickel mine. It's a working mine. And if you go to the 6,800 foot level, so that's just over 2 kilometers, you'll find that there's a scientific laboratory which has been excavated to do science which is looking for rare events, looking for very weak interactions or the occasional event from nuclear processes. So it's a science lab. Where we are at the moment, for instance, we're in a tunnel where we're doing dark matter experiments. So we have 2 detectors around us searching for dark matter. I'll describe what that is in a minute. We also have experiments looking for neutrinos. These are other subatomic particles, and the sort of physics that we're interested in is trying to understand where the neutrinos come from, what the neutrino is, how it interacts with nature and so on. That was an interaction from one of our dark matter experiments just going off there. Okay. And that'll go off every so often as we're going through the interview. So the reason for being deep underground is that the common thread throughout all of these experiments is that we're trying to look for very small, weak signals, very exquisitely small signatures in our detector systems. And so, for instance, a dark matter detector at the moment, if we build a dark matter detector from, say, 100 kilograms of target material, we might expect to see 1 dark matter particle hidden every month or so. And the problem is, if you run these detectors on the surface, there are so many different background radiations on the surface. So when you're sitting in your office, for instance, in a concrete office block, although you don't feel it, you're being bombarded by nuclear radiation all the time. The concrete in the rock, the rock has uranium and thorium in it. Concrete has uranium and thorium in it. And uranium and thorium decay and give off these nuclear radiations, gamma, beta and alpha radiation, and they would interact in our detector and would mask the signals that we're looking for. So it's all about knocking down the background in these detectors, being able to see these really exquisitely small signatures that you're trying to pick up with the physics. So coming underground gets away from one of the core backgrounds that we worry about, and that's cosmic radiation. So if you're on the surface and you hold your hand out, there's a subatomic particle coming from space, streaming all the way through, hits the atmosphere in the Earth and generates what's called a shower of particles. So these things are sufficiently energetic, the more energetic than we could create in laboratories. They're sufficiently energetic that they would actually break apart the oxygen and nitrogen nuclei, and you end up with a huge number of particles coming out in a shower. And on the surface of the Earth, you hold your hand out, you have 1 or 2 of those particles going through your hand every second. Those particles would, again, it's looking in our sort of detectors, they would mask the signals that we're looking for. And so you come 2 kilometers underground, that reduces the number of these particles by 10 million, something like that. So rather than 1 a second going through your hand, it's 1 every couple of months. And that means that you begin to be able to have the sensitivity with the experiments to pick up the dark matter interactions or the neutrino interactions or things like that.
So why 2 kilometers? Why 1,600 feet?
The deeper the better, up to a certain level. And one of the reasons for being here is that we're actually exploiting the success of a previous detector called SNO, Submarine Neutrino Observatory. So there was already some infrastructure here, a laboratory at this depth. And the idea for SNO was basically to go as deep as you possibly could. Yeah. And that's one of the attractions of the Crichton mines. It's a very deep mine. Yeah. So although they're now working a few hundred feet below us, at the time 6,800 was about as deep as you could go. This was 15 years ago. And so the original experiment was set as deep as it could possibly go. And that's where you get the reduction in cosmic ray flux, which allows you to look at the neutrino signals or look at the dark matter signals that we're trying to pick up. So it's a very strange laboratory in that sense. We're obviously deep underground. You're in the middle of a working mine, so we have to take health and safety and things like that very seriously. Hence the hard hats, of course, that we're wearing now. And it has other constraints in terms of the fact that we want to run this facility as a clean room. Coming back to the backgrounds that we worry about in our detectors, mine dust is actually quite radioactive in comparison to the materials that we build our detectors from. So if we threw a gram of mine dust into the SNO detector as an example, it would ruin the detector. You would not be able to pick up the signatures that you're trying to pick up in that detector. And so we have to clean absolutely everything that comes in. So all the materials around us get very thoroughly cleaned as they're brought into the laboratory.
So maybe, sorry to interrupt, but with that in mind, to try to give our listeners and viewers an idea of what exactly we're sitting in. So we're 2 kilometers underground. We're in a corridor right now that's, 10 meters across and 10 meters high? Is that reasonable?
Yeah.
Something like that. So, you know the volume that's been excavated through these labs?
Oh, I wish I could look that up. That is
Sorry. It's big. It's big.
3,000 square meters. But that's the surface area.
So 3,000 square meters of space and 2 kilometers underground.
So
and every inch of that
is absolutely clean.
Absolutely clean.
Yeah. So I have a very dedicated team of cleaners who realise that their job is just as vital to the science as all the physicists.
Right.
So you absolutely have to have everything tied together. You know, it's got to be a clean lab. You've got to get rid of all the radiations, make sure your detectors are background free so that you can actually start to see these systems, look at these very exquisite systems you're picking up. The snow detector, to give you an idea of the scale, the snow detector was an acrylic sphere 12 meters in diameter which had 1,000 tons of heavy water in it, which is then surrounded by several meters of water on all sides. So it's these are large experiments.
Yeah.
The ones we're around at the moment, not quite so large.
So that snow lab that was the original facility 15 years ago, how much bigger is the facility now?
In terms of volume, it's only about a factor of 2.5.
Is that right?
Because the snow detector was so vast.
Okay.
But in terms of area, it's about a factor of 4, something
Yeah.
like that, in terms of the surface area. So we've gone from hosting a single experiment, the snow experiment, to being able to host quite a large number of different experiments looking at a variety of different physics. So the dark matter physics, for instance, was not something that SNO was looking at, but we are now with quite a number of the experiments that we have at the SNO lab. And dark matter is it's one of the core fundamental questions that we're trying to address at the moment in particle physics and cosmology, in that we don't understand what most of the universe is actually made from. So there's something called the cosmological concordance model, which sounds fancy, but what that really means is that we don't understand what 96% of the universe is made from. So there's a massive gap in our knowledge about what actually the universe comprises of. And one of the things that we're looking for here is called dark matter. So dark matter is a material. We know it's out there because of the gravitational attraction and the influence that has on other bodies. Yeah. So the way that galaxies rotate, for instance, their effect on stars. We know that there's a huge amount of dark matter in the galaxy, but we have absolutely no idea what it is. And one of the compelling arguments for building this sort of facility and these sort of experiments is that the particle physics community have problems with what's called the standard model of particle physics. So you'll be aware of the atom is made up from electrons and nuclei. The nuclei are made up from protons and neutrons. And inside the protons and neutrons there are quarks, which go to build up those different subatomic particles. Sure. If you look at that standard model, there are problems with it. And the particle physicists have developed another suite of theories. And one of the outputs from those theories is that there should be a new type of as yet unseen particle, which would be an ideal candidate for the dark matter. So there's this wonderful convergence between astronomy and cosmology, where astronomers have looked at how the galaxy rotates. Yeah. If you're a star at the edge of the galaxy, you're moving way too fast. If all the mass that was in the galaxy is all you can see. Right. And the fact that you're moving so fast and still being kept in the orbit of the galaxy means there must be some other material holding you in the gravitational pull. So that means there's a huge amount of material. You know it's there because it's exerting influence on the star, but you can't see what it is because it's not luminous or dark. Right. So we have this dark matter which it's between 60 and 80% of the mass of the galaxy. It varies depending on the galaxies you're looking at. So 60%, 80% of the galaxy, we don't know what it is, but you know it's there from the influence on the gravitational attraction. The particle physicists, meanwhile, have come up with a theory that the endpoint is, hey, there should be a new particle created in the Big Bang, would be around with us in the right amount. And that's the amazing coincidence, is that if you look at the number created in the Big Bang and the number that you'd need in the galaxy and the universe as a whole, then there's a fantastic coincidence between the two.
And those were calculated independently?
Absolutely.
Okay.
So
very cool.
one is observation,
Right.
and one is theory.
Oh, of course, yes.
So the astronomers and the cosmologists have actually developed this theory by looking at the discrepancies that they see in the galaxy, in our galaxy, in other galaxies, and in the universe as a whole.
Right.
The particle physicists, this is a theoretical prediction. This is
Right.
a theoretical prejudice about what you might expect to see. So there's this wonderful confluence that suggests that there is a new type of subatomic particle, and it goes by various names. It's either called a neutralino, because it comes from something called supersymmetry, or a WIMP, more generically, a weakly interacting massive particle. So we're looking for WIMPs down on Mars, right, which always gets us into trouble. Yes. So this confluence suggests that this really is the reality, and what we're trying to do down here is to look for this new type of particle.
Right.
But to do so, we come back to this question about the backgrounds. So you build very sensitive detectors like you might see in a hospital, where you're looking at other types of radiation. But there, the sensitivities aren't sufficiently good, so you need to make sure that you build your detector out of very pure materials, bring it deep underground so that you get rid of the cosmic radiation, shield it. The detectors around us are shielded, for instance, in water. So the small amount of radiation in the rock and the concrete around us gets stopped in the water shield and doesn't make it through to the detector.
Right.
Whereas the WIMPs, because they travel basically right through the Earth without noticing,
Yes.
there are billions of WIMPs streaming through us, if the model is correct.
Yeah, I was going to say if the model is correct, that's good.
There are billions streaming through us every second, and only one a day or a week actually hits you the nucleus, a nucleus in your body head on, and causes that nucleus to recoil slightly. And it's that energy of the recoiling nucleus that we're trying to pick up in these detector systems.
Boy, wasn't that fantastic? What incredible stuff is going on there at the Snow Lab. Check out their website when you get a chance. I believe it's snowlab.org. Coming up next, Mr. Bryce Drogosh from Muriel. He's going to talk about video conferencing and how to take video conferencing tools and use it in the classroom. No, it's not science, but it is an important way to communicate science to our students. Enjoy.
It was funny because yesterday, we've been doing this, and we announced this product availability, and it's available on the website. So if you want to look at doing this on a Droid device, go to the Droid Market and search for ClickC, and you can get a free account and use it. But the nice parts about it are that it supports the ability to call your existing rooms and your existing deployments. It's unlike FaceTime, where FaceTime, like your grandma, had to get a FaceTime. This opens up the fact that I can call anybody. Right? Anybody that's got a video solution that's already deployed. And in an educational world, one of the things that we've done is we've also incorporated the typical standards that you find in a video call, such as far-end camera control. So, for instance, to get into this conference today, we dialed into a Codium bridge, and the way you get into that bridge for this call is either use far-end camera control or have DTMF tones to enter the 500 number, right? And I have that on my phone, which others don't as well. But if you look at it, we've seen the far-end camera control to be very, not only a nice to have, but a necessity in telehealth, right? At a lot of the health science centers here in the U.S., they have doctors that provide students with health care. But they have to have an endpoint where they can control the far end of the camera so they can focus in on the pupils of the eyes to see if they're dilating, so they can focus in on a rash or something like that on the skin, and so they need far end camera control. So we have that as well. So what I was going to do is I'll join in again with another endpoint. I'm going to call you guys on this is an HTC Evo. It's an Android client. I have this running on the Sprint 4G network here in Allen, Texas. And what I will do is I will dial into there. Because I'm sitting next to my microphone speakers, I will mute and then go to the microphone and speaker of this app.
Well, Bryce is setting that up.
So as you can see, I've dialed in, and I'm going to go to the keypad and go to 500. And join the conference. So you can see I have now joined the conference with my phone. And if you look at the capabilities of what you could do with that, right, is let's say you're in a lab and you have one of these phones, and it's like, for me, I used to go into the electron accelerator labs at the University of Michigan, and you could go in there now and bring a camera like this and be able to show that site. You could be out at a zoo for K through 6 where a sick child isn't there and be able to show them a lion or something like that.
Well, that's it. Hope you enjoyed the best of This Week in Science and Education. I'm sure we'll have a chance to do another one potentially over the summertime. The clips that you saw today really were representative of the incredible research and technology that takes place in Canada on a regular basis. We hope you enjoyed it. For more information about any of those clips or to watch any of the This Week in Science and Education episodes, go to our website, vrock.ca, and click on Watch Podcasts. I'm sure you'll find them entertaining. Coming up on January 4th, we're traveling to Science North. It should be fun. Tune in January 4th, 2 o'clock p.m. We'll see you there. Happy holidays and Happy New Year, everyone, from everybody at This Week in Science and Education.